Thank you. I appreciate your help. Okay, here we go. So, what do you have to do? What should I do first?
Integrate.
Yeah, well, that's what we're doing overall, but what should I do first? What topic is this? What topic?
This is
Partial fraction decomposition. So what should I do to the bottom?
Factor.
I should factor the bottom?
Yes.
Is it factorable?
Yes.
Into what?
It turns into x plus.
Yep, 2x minus 3 over, girls, showing when, x plus 6. Like that, right? So then we need to write a over x plus 3 plus b over x plus 6 is equal to over x plus 3 times x plus 6. Exactly. So what does that tell us? It tells us that a times x plus 6 plus b times x plus 3 is equal to 2x minus 3. So what's that magic number that we like? Like, what's the first one? X equals, how about negative 6? And if x is equal to negative 6, we end up with negative 3b is equal to negative 9. So what does b equal? Did I do it wrong?
Negative 15.
Oh, it's a minus. You're right. Thank you. Thank you. Equals negative 15. That's my fault. Negative 15. So b is equal to 5. And then, let's change it up here. So x equals what? How about negative 3? So we end up with 3 times a is equal to negative what? 3 times a is equal to what? To negative 9. Yep. So a is equal to what? Negative 3. So now we know we're dealing. Now we're just going to do the integral of what is it? Negative 3 over x plus 3 plus 5 over x plus 6 dx. And how many integrals is that really? I mean, you're just doing two of them. You're doing negative 3 times 1 over x plus 3 dx plus 5 times the integral of 1 over x plus 6 dx. So what is that going to be? Negative 3 times ln of what? Plus 3 plus 5 times ln the absolute value of plus c. Is that up there?
No, you have to move things together.
Oh, they combined it?
Yeah.
Oh, I see what... Oh, I see what... Yeah, fine. So what they mean by this is, look, you can turn it into ln of x plus 6 to the 5th minus ln of x plus 3 to the... And it's this. Did it keep that in there? It did, right. And now you can divide, so now it's just log rules. So now you have x plus 6 to the 5th over x plus 3 to the 3rd plus c. Do you remember that, kids? ln a minus ln b is equal to ln of a over b. Yeah, I'm telling you right now, this rule right here. Oh, you also know that n times ln of a is equal to ln of a to the n. That's just a log rule. You can do that. You also know it like this. I mean, you can, yeah, just go with it, okay? Log rule. So, I mean, that's kind of annoying because you have to finish it with some specific knowledge. But that being said, there aren't that many things that are super important to working with logs, and these are two of the most important ones. I mean, you also get a pretty big clue here. When you look at this, you know it's going to be x plus 6 and x plus 3, right? So which ones can you immediately eliminate? C is gone, right? A is gone, and then you know, maybe if you stick around D, but you know it's going to be broken up. But then you also know there's going to have to be a negative in there, which okay. I mean, it keyed us into the fact that there was something else to do. So here's some importantness right here, but you can definitely do that. Okay, it says the position vector for a particle moving in the xy plane is that thing right there. So that's the position. The slope of the tangent line to the path of the particle at time equals 4 is what? So if that's the position, what do you have to find? Yeah, so if you, you haven't done this before, this is the position vector. You're not doing dy dx, you're doing the rate of change with respect to time, right? No, you don't have to split it, but like if this is the position, we haven't covered this yet, but I bet you could figure this out. If that's the position, what's the relationship between position and the velocity? What do you take? Take the derivative. So what's the derivative of this right here? 10 over what? 1 plus t. And what's the derivative of the second part? 8 over what? Root t, exactly. So this right here is the what? That's the velocity of the particle, right? Do you agree with that? So here's some of you have taken physics, so you might already know this. It's asking you for the slope of the tangent line. So what do we do? Actually, you don't. I'm sorry, it's not even asking you about speed. So if we want the slope of the tangent line at time equals 4, what do you plug into the velocity at this point? The time. What is the time?
4.
The time is 4. So if we plug in the time at 4, what do you end up with? 10 over, so at time equals 4. 10 over what? Comma, 8 over 2. So you end up with 2 comma what? 4. And keep in mind, this is a vector, not a point, right? A vector, not a point. It's not a point in space. This means this is the x and this is the y. So what is slope? Change in y over what? Change in x. And this is more accurate because it's a velocity. This is the change in position. So what is this going to equal? So if we want the slope at time equals 4, what's that going to be? 4 over, which is 2. Again, we haven't done this yet, but it is 2.
I did it with dy dx.
Okay, then there's another. Yeah, sure. You can do. Yes, you can go and do it many different ways and get it. That's fine. This is just we haven't done this yet, but I wanted to kind of tie it into something you might have seen before. Is bounded in the first quadrant by x and y axes and the curve 15 minus e to the x. So one thing you could do is draw this out. So it's bounded by the x and y axis. It's in the first quadrant. What is when x is 0, what's y? When x is 0, what's y? So what is it? What does it hit? 0 comma 14. Do you agree with that? And as this goes on, as x gets huge, what happens to it? It goes really far down. Does it ever get to, what's e to the billion? Huge, right? When does this cross the x-axis? So 0. This is more than we need, but e to the x, right? So when does e to the x equal 15? So that's ln of what? 15 is equal to x. Ln of 15 is going to be like 2 and something, right? But the point is, it's a curve going down, right? Do you agree with that?
Well, I mean, this is on the calculator.
Yeah, I know. I'm just saying, I'm trying to get a picture of it. It doesn't?
No.
No? Oh, is it?
It's concave down.
Oh, it's concave down. Okay, how do you know it's concave down?
Because e to the x is concave up, and therefore...
Oh, well, hold on. Look, let's just do it. How about you do it definitively? Okay, what's y prime going to be? Negative e to the x, right? So what's y double prime going to be? Negative e to the x. And that is always going to be what? So right, it's going to be concave down. But this thing is always going to go, the derivative is always negative, so it's always going down, so you're right. So it's like this? Okay. So, anyway, I just wanted to show that. Well, the point is, this is the base you're dealing with. Do you agree with that right here? This is the base you're dealing with. It says each plane cross-section of the solid perpendicular to the x-axis. So perpendicular to the x-axis. So this is, do you agree that that's perpendicular to the x-axis right there? So you're making cuts like that. Is a semicircle with diameter across the base. So what you're looking at is at each of these cross-sections. So if I did another one right here, you kind of see what's going on here?
I just really didn't understand what you were asking for.
I totally understand. You might not have seen it. That's fine. But do you understand what they're asking for now?
Well, no.
So look,
I knew exact kind of problem, but just the language.
Okay. Yeah, so do you see what I'm trying to do here? So it tapers to 0 right there. Do you agree? And where's the biggest one? The biggest one's going to be right there, right? Keeps going. This is not that bad, kids. This is totally not that bad. So it's asking, what is the volume of the solid? Now, what's the area of a semicircle? 1/2 pi r squared. The trick now is just finding the radius of each of these semicircles. What is the radius of each of these semicircles? Half of the function. The radius is going to be 1/2 of what? Exactly, 15 minus e to the x. So what are you integrating from? 0 to what? 0 to the natural log of 15 of, put pi on the outside, r squared. I'll do it. Yeah, I just want to put it all together. It's going to be 1/2 15 minus e to the x, all raised to the 2. And then what's the thickness of each of these? Oh, it's, sorry, 1/2. Thank you. dx. dx. Are you okay? Do you understand now with this? It's a challenge. These cross-section ones are not that bad. You just have to usually, I can tell you the most annoying thing to me about the cross-section problems is sometimes constructing, the trickiest part is by far for me, constructing the area of each cross-section. For example, the one that's most annoying to me is the ones where it might ask you, the cross-section is an equilateral triangle, right? And the problem with that is you need the. Do you remember what the formula is for equilateral triangle in terms of just the side length?
It's that times
S root 3 over. I think it's 4. I think it's S root 3 over 4 or S root 3 over 2. But the point is, do you definitively remember that? No. When
S squared root 3 over 2.
S squared root 3 over 2. That sounds better. I knew there was another factor of 2 in there. But the point is, did you remember that? No, it's out there, and usually this is what I do. I'm like, okay, I've got the equilateral triangle. Oh, it blinked again. I go to a random page, but look, I don't know why it jumps like that, but like, okay, I got an equilateral triangle. When you see me just, it's like this, I know that this is S, I know that this is 1/2 S, so you know that, I'm like, okay, I figure it all out, right? The point is, if I ask you that, I usually give you the area of an equilateral triangle as opposed to side length. The problem is, in my opinion, calculus problems should be about calculus, not remembering a specific formula for a specific shape. You generally, I mean, it's fair game for equilateral triangle formula, so you might want to remember it, but semicircle, you can derive it. You guys should be able to derive it. It's not that hard. Base times height, and you find the base in terms of the side length. Exactly what I was just showing you. Just be prepared for a weird kind of shape like this.
The shape would not
Directly follows. So for example, if I start with this, you have x equals f of some function of t, and y equals some function of time, t being the index variable, and you have y equals f of x is the path for that particle without the index variable. If you know that x is equal to f of t, so if you plug that in, you know that y is equal to capital F of what? Little t, like this.
Yeah.
Now, Tomas, if I were to take the first derivative here with respect to t, what is dy dt going to be equal to? F prime of f of t times f prime of t. Do you agree with that? Okay, so what we can now do, what did you know f of t was equal to? Well, f of t is just what? What is f of t? It's just what? So you know dy dt is equal to f prime of times, you want to do that one now, that's good, dx dt. Girls? So now you know that f prime of x is equal to what? Dy dt over dx dt, exactly. All that tells you is if you want to take the derivative of y equals f of x and you have the parameterization of the function, you can find the derivative directly. You take the derivative of y with respect to t, and you divide it by the derivative of x with respect to t. Yay! Very nice. Are we okay with that? Okay. To clean this up a little bit, it'd be nice if this was like, you know what I mean? Like definitively separated, especially since you look at it and you're like, what is dt dx? That's not the second derivative, which is great, but what's notable about that expression? Like, how is this expression different than what you might assume it would be? Okay, when we did this one, it seemed pretty logical. You did dy dx, so you did dy dt, and you divided by dx dt, correct? Look at this one. What is this one not? Come on, be serious for a second. Yeah, exactly. So if you follow this logically, you would think it would be the second derivative of y with respect to t over the second derivative of x with respect to t. Is that the case?
No.
No. What is it?
It's the derivative of the derivative.
Yes.
The derivative, yeah.
And the way you get this is simply, look, this is definitely true. Instead of putting in y right here, you put in dy dx. You literally put dy dx right there, and look what happens. It's the same thing. You have d dx dx, you've got d squared, you get dy dx, and then you substitute it up here. Instead of y, what do you put in? Dy dx. So it's really important that we do that very, very carefully. You don't just do the derivative twice. You do the derivative with respect to t of dy dx, and then you divide it by dx dt. It's just really important that you notice it. Exactly. Well, we're going to do some more of them. A curve C is defined by the parametric equation x equals t squared, y equals t cubed minus 3t. Show that C has two tangents at the point 3, 0, and find their equations. Show that as two tangents. We found tangent lines many, many times. How do you find tangent lines? Guess what? And we know that t cubed minus 3t has to be equal to 0. So we know that that's t times what? T squared minus 3. Agree with that so far? So that means that, what is that? And that's going to equal 0. So t is going to be equal to or plus or minus root 3. Exactly. So that there are two different times that we're looking at, which are, so its time is equal to plus or minus root 3. So we're doing dy dx when x is equal to, not x, sorry, t is equal to, let's say root 3 first. What's that going to be? 3 root 3 minus 3 over, so that's going to be 9 minus 3 is 6 over 2 root 3. So it's 3 over, and you can keep it like that, that's fine. You don't have to rationalize. And then, dy dx when t is equal to negative root 3, what's that going to be? Yep. We can simplify it more. You can just leave it like that for now, and we'll go back in a second. Yes, that's correct. So what do you end up with? You're squaring a negative, but you end up with 6 over what? Negative 2 root 3, which is just going to be negative 3 over root 3. And yes, you can multiply by root 3 over root 3 to rationalize. And what do you end up with? Negative root 3. Negative root 3. And what does this end up with? Root 3. So you have the slopes. These are the slopes at the 2 points. At the 1 point, right? So when at the top one here, let's use blue, I guess. At the top one, the slope is root 3, and the point is 3, 0. So they asked you for the equation, right? So it's going to be y minus what? 0 equals root 3 times x minus 3. And then this one's going to be y minus 0 equals negative root 3 times x minus 3. Exactly. We good so far? Which one do you want to do first? Horizontal? That's exactly, because what do we have? We know that dy dx is now equal to, what was it? 3t squared minus 3 over what? Over 2t. So we know it's going to be horizontal when? Yes, horizontal when 3t squared minus 3 is equal to 0. So when's that going to happen? When 3 times t squared minus 1 is equal to 0. So that's time equals plus or minus 1. And we know we're not done yet, but it's vertical when what? 2t equals 0, which is when t is equal to 0, right? So the point is, it's not asking for the time, it's asking you for the points on the curve. So then you have to go back, look at your parametric equation, which says that x is equal to what? T squared, and what is y equal to? What was y equal to? T cubed minus 3t. So at plus or minus 1, so when t is equal to plus or minus 1, what does that mean about the points? It's going to be 1 comma negative 2, and negative 1 comma, it's going to be negative 1 plus 3. It's going to be positive because I can't square anything, that's correct. But it's going to be negative 1 plus 3, so it's going to be 2. Is that correct? Right? So we know the tangent lines are horizontal there, and vertical at time equals 0. So time equals 0 means it's just going to be 0 comma 0. That's kind of cool. Okay. Determine whether it's concave upward or downward. So if we're talking about concavity, what do we have to look at? Second derivative.